Okay, so I'll basically be going through this code that I discussed in the um, class yesterday. And I'll walk you through this, and I'll obviously share this code with you as well so you can play around with it in your own time. Okay. Um, so we're basically going to start with this program, which is basically um, you could just say is just uh, the sequential program. Right? It has only one thread. It has a main module, right, which is here, and then it has this function, which I'm calling function underscore thread. Now the name is, it contains the word thread, but that's not going to turn it into a thread. I mean, or a separate thread at least. What happens here is you have the main module and you start the timer when your program starts. Then you just call the function, you give it a name, call it thread A, and that function basically all it does is it goes to sleep for 5 seconds. So it's kind of simulating some I/O type of process where you send out a request and that request kind of takes a little bit of time to kind of get back. And as soon as that request is entertained or it completes, then you get thread duration. So how much time did the thread take to run? And then in the main function, you also, after you kind of the function completes, you calculate the duration that the main thread or the main module was running, and then you just print that time. Now, this is basically just a simple sequential program where you have a main module, it just calls a function. The function kind of uh, goes to sleep for 5 seconds, wakes up, prints the time that has passed since the start of the program, and then you go back from the main function, sorry, from the function to the main module, and then the main module again, all it does is prints out the time that has elapsed since the start of the program. Okay, so let's just quickly run this. And you can see the main thread, so function underscore thread started with thread A, so that's just the name of this thread. Um, function ends after 5.0155 seconds. And then you can say immediately after that, you can see that within like probably a millisecond or so, your main also ends, right? So this is just a sequential program, and this is what you would expect to happen, right? That you start your program, and then um, all you have to do is, um, uh, you know, it just will run and it will stop after a little bit of time. Now, if you want to use this code, I can try to send it in the chat. I'm not sure if the indentation will work. Let me just send this as a file. So let me just copy paste this. So if people want to kind of make changes as we go along, so let me just copy paste this inside a file and I'll share that file with you. And obviously I'll upload this um, to Blackboard as well, so you can play around with it later. So okay, so let me just share this with you in the messages. to share a file. Okay, it allows me to share only PowerPoint or PDF type of files. Okay, is there another way? No, looks like it only allows me to share PDF. Let me see if I can copy paste it in the text, and let's see if that works. I hope it kind of preserves the indentation. Okay, you may have to um, work with the indentation a little to make it work. I don't know, it will take too much effort. I mean, anybody wants, they can copy paste from here, but the indentation doesn't really look that nice. So, yeah. Um, so, why don't you guys wait until the end and you can maybe copy it, or let me just upload the file. So, let me just upload this to Blackboard so you can download it from there. Just give me 1 second. So, yeah, I'm just going to upload this. I'm going to create a folder for Lab 5. Okay. Um, so I've created a folder um, for Lab 5. Lab 5, you have lab code, and then from there you can download this threading.py file from there. So I'll just give you maybe um, a few seconds to download the file from there. Okay, so now that you have this file, there are a few things that you can do with it. Just give me 1 second. I'll show you. So what you want to really do is to kind of create a thread. Um, okay, sorry, there's a little bit of an issue with my screen sharing. Okay. Uh, Apologies, it's a little early in the morning. I got up just a few minutes ago. Okay. Um, so I have this open here. Okay, so now if I want to kind of make this um, kind of like a threaded type of an application where I want to, let's say, if I want to execute this function inside a separate thread, what I need to do is first I need to import the threading module. So if you've already copied or downloaded the file from there, um, you can basically um, make modifications to your program. And in fact, let me put this inside a temporary file. So we'll keep the original file with me. Okay, so inside this, what you will need to do is you will need to import threading. So once you've imported threading, you have the threading module. What you want to do is you want to put your function underscore thread, and you can, what you want to do is put it inside a separate thread. And the way to do that is um, you can first comment this function out. Um, and what you want to do is, let's say you want to create the thread and you want to give it the name thread A. And then what you need to do is call the threading package and create a threading object, right? So to create a threading object, you will need to call the threading package, and then from that threading dot thread. So this basically will create a thread object, and in that thread object, what you want to do is you want to um, basically execute this function fn underscore thread. So this is your target, right? So your thread object basically is going to run this function. So that's why this is your target. And then if your target basically requires an argument, you can pass one or more arguments to it like this. So this is your argument. Uh, and the argument is just the name that you're going to give the thread. So if I call it thread underscore A, what that will do is it will create this thread object for me. Okay. Now, if you're typing this along with me, you should be able to kind of see how this runs as well. So once you've done that, you have thread A, and that is, so what you have is an object, a thread object, which once you start that thread object, it's going to execute this function with this argument. Okay. So if you want to, so now that you've created a thread object, you need to start the thread object. And for that, what you need to do is you need to write down thread underscore A dot start. So you call the start method. And what that start method does is it basically is going to start this thread object. So thread object basically is the object that you can trigger to create this new thread. And so what will happen is now you will have a separate thread to execute this function. So now your program kind of becomes multi-threading, and so it should run now. So let's go ahead and run this and see what it does. Now notice here that first the thread function finished in the sequential version, right? Thread function finished after 5 point something seconds, and then a little bit after that the um, main basically finished. Okay, so let's run this and see what happens. Right, so you can see immediately as soon as you start your program, your main module ends immediately within, you know, 0.0054 seconds, right? So, but your main thread basically runs, keeps running, and then it ends after 5 seconds, right? You can see that even though the main ended, your program was still working, and your thread actually ended after 5 seconds, right? Because it went to sleep, and then it woke up, and then it kind of finished. So again, now because your function underscore thread is on a separate thread, your program doesn't really have to wait for it, right? It can go ahead and complete stuff or do its own thing and then finish, and then the thread can kind of finish in its own time. And again, there are places where you actually may require, you may want this to happen, and there are times when you may not want this to happen. But by default, Once you start a thread, you assign a separate thread to something, and that thread kind of starts out and then it finishes. And then whatever comes after that point where you start the thread, by default, that is going to keep going on the original thread. So you have two threads, one thread for the main module, and then you created another thread for this function. So these are two separate kind of independent threads now. So once you trigger this one, and once the kind of compiler sees that this one went to sleep, it'll say, okay, I've started this one, it'll complete in its own time. And then what it'll do is it'll just keep going with the rest of the program which was on the original thread, and it'll go ahead and complete that. I hope that makes sense. Okay. I hope if you've copied the code, you've kind of tried this out yourself as well. Okay. So now that we've done this, but let's say we want the program to actually wait for the thread to finish. And if you want the program to wait for the thread to finish, then what you need to do is you need to call the join method, right? And what the join method does is it basically will wait or will make the original thread or the main thread wait for thread A to finish or terminate, and then you can think of join as rejoining the program, right? So it rejoins the main module. So what with join, you're basically going to make the program wait for thread A to finish. Okay. So um, let's do this. In fact, before I do this, let me just, again, in case you missed it, let me quickly show you what the program did last time without the join. So once we do not have any join, if we do this, you can see main ends immediately, and then after 5 seconds, your thread A basically ends after that, right? So function thread, which is on thread A, ends after 5 seconds. And there is no line over here between these guys, or new line, because this guy's kind of ended immediately after calling the start function. So it immediately ended before you kind of had the chance to go to the new line. Okay, now let's uh, make the program wait for the join function. Now what will happen is your thread will start and your main will wait for the thread to finish. Now you see it's waiting. Thread A started, it's waiting, and now um, after thread A finishes, main ends after that, right? So the join method is basically making the main program wait for the um, for the um, for the thread um, that you told it to wait for, right? Now there may be a situation where you have multiple threads in your program, and you may want the program to wait for those multiple threads, or you may want the program to wait for some of the threads and then not wait for some of them. And then what you can do is use or call the join method on threads for which you want the program to wait, and not call it for threads which you do not want it to wait for. Okay, so I hope it's clear so far what we're doing, right? Um, so I think there's one more feature of join that I probably just want to quickly show you guys. So let me bring that up. If you kind of read the documentation of Python, right, and I encourage you to do this. Um, so you kind of come to this part where you have you kind of you have the start and the join, and all these methods are basically being described, right? So for the threading class, you have these methods that are available to you, and so the join method. So this is the join method, and the join method in the documentation, you can see it says wait until the thread terminates, right? Now, why would they call this the join method, and then in the description they say wait until the thread terminates? They probably should have called it something like wait or wait for thread or something. but I don't know, they just called it join. So that's why I like to think of it as wait for the thread to rejoin. That's the way that I kind of like to think about it. So because otherwise the name dot join doesn't really give you any idea of what this method does. So you have to kind of think about it as wait for the thread to rejoin the program or something, right? Or rejoin the current location in the program. Now, one more argument of this is you can see is it has one argument which is called a timeout, right? And by default, timeout is none. If you look at the documentation, what it says is when the timeout argument is present and not none, it should be a floating point number specifying the timeout for the operation in seconds. So what that basically does is you can specify. So join function has a timeout parameter or argument, and you can use it to kind of tell the program that, okay, wait for this for these many seconds. So let's suppose if you want the main to um, wait for a thread for a maximum of 2 seconds, you can put that down here. So you can write timeout is equal to 2.0, and what the main will then do in that case is um, it'll wait for 2 seconds, and if it does not rejoin after 2 seconds, it'll just continue. And then the thread can kind of continue in its own time. Now, timeout does not mean that timeout of the thread, so the thread basically terminates. Uh, so so the thread will still continue. The thread will not itself, I think the thread does not finish. The thread does keep going. It's just that the main is not going to wait for it after the timeout has kind of expired. Let me actually try this. So let me put timeout is equal to 2 seconds, and then see what it does. Okay, so let's call this. So you can see main ends after 2.045 seconds, and you can see that the main thread did not terminate. It kept going, and it ended after its original time of 5 seconds, right? So with the timeout, what you can do is make the program move on. So if you wanted to wait for like a certain amount of time, you can kind of control that using the timeout parameter, okay? And I think you don't even have to specify this equal to timeout because this is only one parameter. So it should still work with that. Yeah. Okay. So this was the case for a single thread where you have like one thread, you want one function, you put it inside one thread, and then you kind of execute it. And now in this case, you may be thinking, all right, well, we don't really get a lot of advantage by making this program multi-threaded because it still kind of runs or still consumes the same amount of time that um, was consumed when the program was sequential, right? So you don't really get any advantage from introducing concurrency here, which is true. Um, and the reason for that is that, this example is originally given or is designed to kind of give you an idea of uh, how to create a thread, how to start a thread, how to join a thread. Now, if you want to see the advantage of concurrency, what you have to do is you have to um, basically add more threads. So if you can create more threads and then call those threads concurrently, that's the time where you'll actually um, see the advantage um, of concurrency. Okay, so let's go ahead and do that. So I'm now going to kind of make this really multi-threaded. So I'll have multiple threads that I'll probably put in there. And then call those threads. Okay. Right. So what I can do is, so one way I can do that is I can call this thread A, right? and let me say, call this function underscore thread A. So I have thread number 1. So this I'll put in thread number 1. I'll create another function. Again, maybe this one is, I call it function underscore thread B. And then finally function underscore thread C. So these are going to be 3 functions that I'll put in 3 different threads and run these as 3 independent threads, run these concurrently, and then I'll see how much time the program takes overall. Okay, each thread basically, all it does, it prints its name, and then sleeps for 5 seconds and then tells you when it wakes up. Okay, so now that I have 3 threads, I basically need to create 3 thread objects for these threads. So also I need to change the name here, which is thread A. Create an object for thread B and then another object for thread C. So this one will be thread B, this one will be thread C, um, thread B, thread C, and then obviously I want to give them different names as well. Okay, and then of course you can start these threads and then you can wait for them, ask the program to wait for them as well. So thread A dot start, B dot start, and then start thread C as well. And then similarly wait for threads B and thread C as well. C and B. Okay. Now, how much time do you think this program is going to take? We discussed in class yesterday. You're kind of creating 3 thread objects, right? Uh, so what that means is each of these threads is going to run concurrently on an independent thread object, right? So what that means is that if this was a sequential program, it would run and finish in about 15 seconds. But because this is uh, um, because this is being concurrent, so you're running this concurrently. This is not sequential. You're putting every thread or every function you're putting inside a separate thread. So you put thread A inside a separate thread, this function inside another thread, and this function inside another thread. So these are 3 independent threads that run concurrently or run at the same time. And so what that means is because they're running simultaneously, you should not take more than too much longer than 5 seconds, right? So instead of 15 seconds, you actually should finish in somewhere around 5 seconds. So let's go ahead and see if that is actually the case. So all 3 threads started and you're waiting for these 3 threads, and you can see that again slightly more than what you had with the single threaded version, right? But not too much longer. So this additional overhead that you get may be due to the overhead that you get from managing these threads. But overall, you can see that you now see the advantage that you get by adding the extra complexity to your program. By introducing threading, uh, now you run this program and this program finishes in 5 seconds instead of 15 seconds. Now, one experiment that you could do is, and maybe I'll give it to you as your lab task, one experiment that you could do is make this program sequential. So don't put these guys in threads um, and then run them, so without threading. And what you will actually see is that this guy will run in, it will finish in 15 seconds. In fact, if I just comment this out, let me just comment this part out. And let me just call these guys sequentially. Um, and then let's see what happens. If I'm not using multi-threading, so if I use thread underscore A, name thread A, let's go ahead and see. If you want to comment a whole block out, you have to use these double quotes 3 times and then um, put them at the end where you want to comment out the whole block. It gets like this. Okay, so B, and then finally function underscore thread C. Okay, so now what you're doing is you're calling all these functions, but now you have just one thread. Even though you're importing threading, right? You can see that this warning that you get threading imported but unused, right? So it's imported but it's not used because you didn't, right? You're just calling these functions. You're not putting them in separate threads. Just calling them sequentially. So what will happen is the first one will complete, second one will complete, and then the third one will complete. Now this guy will take a lot longer. So let's go ahead and see how much time that takes, right? See the first one, you're waiting for the first one. It'll complete after 5 seconds. Now the second one starts. It'll complete after another 5 seconds. And then you see overall you get around 15 seconds, right? So you can see that you kind of added a little bit more complexity to your program, right? You introduced these 3 threads, but that's the advantage that you get with concurrency. Okay, so this is what you're kind of getting. All right. So make sure you kind of understand these programs. This kind of goes out for all students who are taking this course, both in the male and the female section. Um, you could get like a small multiple choice on the exam or some questions like these on the exam where you kind of, you have these sort of things. So I mean, you get a program and then you're asked, okay, what is going to happen? How much time is it going to take? Things like that. It may not be exactly identical to this, but something that tests similar concepts, right? Or you may be asked to write something like this as well. Maybe given a function and then how do you kind of write the main package or main module for this function or something like that, using multi-threading or using some other kind of approach. Okay, so that's what happened. Now, one more thing that I just want to quickly point out here is you don't have to create 3 separate functions and then put them inside 3 threads. This I've kind of just done to kind of make this part easy to understand. Um, what you could have done is you could have just had like one function and you could have called it with different arguments and put each call inside a separate or an independent thread, right? So so let's suppose I want to create a function fn underscore thread and I'm giving it this argument name. Now what I could have done is I could have given it the name or the argument thread A and put that inside one thread. And then I could have called this same function again with a different argument and then put it inside another thread, right? Uh, and I would not really have to kind of copy paste this and write these 3 separate functions for these threads, right? I can call the same function inside 2 different threads as long as as long as that's what I want to do. So let me quickly illustrate that. So instead of having these 3 functions, what I want is, what I could do is create 3 independent thread objects and then call this function using those thread objects. So what I could do is, I have just one function, function underscore thread. And so I call this function. And the first time I call it, I give it the argument thread A. So the first object that I create is thread A. Target function is function underscore thread. And the argument is thread A. Now, the second thread that I create, again, I could call the same function in that, or put it in that thread object. So target for all 3 is the same, right? For all 3 threads, the target is basically the same function, function underscore thread. Okay. It's just that the arguments are different, and I don't have to make the arguments different, but I'm making the arguments different um, because I mean I want to see what thread runs at what time. Okay, and then other than this, your entire program basically remains the same, right? So you have thread A, thread B, and thread C, um, and then that's it, right? So let's go ahead and run that. So we don't have to have like separate threads, functions for each thread. I mean, I have the same function. I'm just calling it inside a different thread, and I can give it a different argument. Um, if I want to. So yeah, it will generate three threads. Again, this is the thread part, right? So you have the first thread object, you have the second thread object, you have the third thread object, and then this part basically creates three threads. Okay? No, the function name, so the target function is the same, but the name that I'm giving it is different, right? So for thread B, the name that I'm giving it is thread B. Or I could also call it like the second thread. And then thread C, I could give it like I'm giving it a different argument, right? But all three will run on different threads because I'm creating three separate thread objects. Okay, so I don't have to have like three separate functions for this. I can just call the same function, um, apply like inside a different thread, and it'll just create a different instance and create a different object and run that function inside that thread. Okay, so how much time will this take to run? 5 seconds or 15 seconds? Yeah, I'll take 5 seconds, right? Yeah. Thank you, Isha. Because again, I have three threads and they're running concurrently. So let's go ahead and run that. You can see all of the three started. They're in wait for one of the other guys, and you can see that all three threads kind of finish in very quick succession, and you can see that the main also ends after 5 seconds. Uh, so you didn't have to like create like a separate function for each of these. That's just what I wanted to illustrate with this. Okay. Um, right. Okay. So now the next thing that I kind of want to illustrate after this, just give me 1 second to kind of see what's the next concept that I want to cover. So now that I've covered these, um, okay, now the next thing that I want to do is you can see that when you're actually managing these threads yourself, your code does get a little bit long, and you have to manage each thread yourself, and you have to start it and join it and do stuff like that. Now, if you remember async IO, we talked about um, a package which was called concurrent.futures. We use it in async IO as well. And that package, what that basically will do is actually um, will make managing the threads a lot easier for you. So that's a relatively new package which basically works for both async IO and for threading. And you should try to use that as much as possible because it really will make your program um, a lot more simpler and a lot shorter as well. So what you need to do is you need to import concurrent.futures, right? So you can write that down in your code. So you can just import concurrent.futures and right. So one thing I want you guys to note is notice how long this program is right now, right? So you have like you're going up to line number 38. Okay. Now with concurrent.futures, one of the advantages is that that's a package that you can call and it will kind of manage these threads for you. So it will kind of do this whole thing for you, right? So let's see how that works. So what I can do is delete all this part, and what I can do with concurrent.futures is I just basically call a context manager, so I can make the concurrent.futures my context manager. So I use the keyword with, and then I write with concurrent.futures, and then I write thread pool executor. Again, if you remember async IO, you use the thread pool executor with concurrent.futures as well, right? Now, the nice thing about concurrent.futures is that in addition to thread pool executor, it also has this other process pool executor. So concurrent.futures basically works or supports both threading, it supports async IO, and it supports multi-processing as well, right? Um, and so we have thread pool executor, and then what we do is we also specify how many threads we need. So if we write max workers is equal to 3, so it'll say, okay, I need to get 3 threads, and then I need to write this as executor, or you could just write E here, it really doesn't matter. And then write executor dot map, and then here you specify what function you want to apply to it. So what is your target function? And you can write what is the target function? It's function underscore thread, right? And then in the next, you can basically argument, you can specify what arguments do you want to send it. So let's suppose what were the arguments? The arguments were just the name. So I can say thread A, and then second argument in this list will be, okay, what is the name for the second thread? I'll call it thread underscore B, and say thread underscore C. These are the 3 threads that will run, and that's all I need to do, right? So notice how short your program got. So you were going up to line number 39, and we kind of deleted those 10 lines. And all we need to do is we just replace those start and join and everything. We just replace that with this thread pool executor. And notice now that you don't really need to import the thread, right? Threading is imported, but is not used because you're using thread pool executor, so it'll manage the threads and everything for you. So you can just remove this. You don't need to import threading anymore. Okay. Yeah, that's the objective, right? So we want this to, so we're using like 3 max workers, right? So that means we're using 3 threads. We have 1 thread for each of the thread objects that we're creating. So yeah, I think this should run in 5 seconds. So let's see what it does. So let's go ahead and run this. So all 3 threads start at the same time, and then see how much time it takes. So it took around 5.04 seconds. So I think maybe it took a little bit longer than the single thread with the threading version. Again, this is not necessarily a very reliable number because it can vary from one run to another. But you know, even if it takes longer than the single-threaded one, even if it takes a little bit longer, the code is a lot simpler. In fact, I can run it one more time and then see how much time it takes. Yep. So you can see now it kind of runs around 5.02 seconds. So a lot simpler code and a very elegant solution. Now, I think one of the recommendations that is generally given is that if you can use concurrent.futures, you should use it, right? And avoid kind of directly managing your threads or directly managing your async IO yourself. I think one of the issues is that some packages may not be supported or generally not supported by by concurrent.futures, and in that case, you have to then switch to directly managing your threads or working with async IO directly. So use this wherever possible, and then if it's not possible to use this, then you already know how to manage your threads yourself or async IO. It requires a little bit more effort, but you really appreciate this guy once you've done those, right? So after you've actually managed the threads yourself, after you've actually written a few programs containing async IO, then you really appreciate the advantage that you get, uh, or really appreciate the fact that concurrent.futures actually exists for you. So it's something that is available for you. Okay. Uh, so so I think we've covered a lot of this now. The examples in the book, um, are, are similar. So I'll kind of quickly go through those. The examples in the book is for chapter 12. I think it's chapter 12, or is it chapter 14? So I think it's chapter 14, the chapter on deadlocks. Let me open that. Sorry, chapter 12. So examples in chapter 12 of the book mainly talk about deadlocks. So they basically illustrate deadlocks and what they are. So they give you a few examples. So I'll quickly go through those examples as well, just to kind of illustrate what deadlock is and how it can occur. You've kind of covered the theoretical concepts, covered them to some extent in the class, where you kind of talk about this three philosopher or five philosopher, or the dining philosopher problem. So, but in context of thread, when you have multiple threads, how can you get deadlock? You can get deadlock if, let's suppose, um, this thread, so there are two resources, and thread one basically gets access to this resource, and let's suppose this thread 2, or rather, okay, so these are threads. So you have process A and process B, and then you have resource 1 and resource 2. Now these process A and process B both require access to both resource 1 and resource 2, right? um, in order to finish. Now what could happen is, let's suppose process A gets access to, or gets control over resource 2, and then process B gets access to resource 1. Now what could happen is that, if process A requires both resource 1 and resource 2, if it does not, if resource 1 is not available, it has resource 2. So if you're not careful with the way that these processes are managed, what could happen is you get resource 2, but you're waiting for resource 1. And what happens is process B gets access to, or gets control over resource 1, but it's waiting for resource 2. So both these guys need two resources, and they're waiting for the other to release the other resource. And it kind of goes on like this forever, right? And that's basically what happens with deadlock. So we'll kind of illustrate this in the examples of the book. So I'll quickly kind of copy paste these examples from the book and quickly show you how they run. You should not have a hard time um, understanding these. The only difference here is that we're introducing the concept of the lock, right? So far we haven't really been using locks inside our threading examples, but let's suppose if you want to use a lock, what the lock basically allows you to do is it allows you to kind of um, you know lock down a resource. So if there is some memory location, or there's some other resource that is not equal to the number of threads, then what can happen is you will um, you'll have to kind of wait, right, for these. And so we'll look at this example. Just one more thing came to my mind as far as async IO is concerned. One experiment that you could do is maybe change the number of max workers to 2. If we change the number of max workers to 2, let's see what happens to the execution type of our program. So if we have two threads, now you can see two threads started at one time. We have two workers, and then one of them finishes, and so once thread A finishes, um, then the other thread starts, right? So thread A finishes, so one of the threads finishes, I didn't put the name here, then thread C starts, and then so overall you can see now, because you had two threads, your program will take around 10 seconds to finish, okay? Because you're using two max workers. If you use 3, then of course you have one dedicated thread for each of them, and it should finish in 3 seconds, in 15 seconds. So this is another thing that you need to kind of figure out, right? So how many threads threads do you want to use for your system and all that stuff. So that's why we have this concurrent or futures over here. Okay, so an interesting thing that we just learned. So the next thing that I want to do now is just look at example one. So let me just quickly open example one. So the concept of workers is, Hisham, workers in concurrent.futures is how many threads are you going to be running concurrently, right? So how many threads will be run at the same time. So if you make them two, that means you have two threads that can run concurrently at the same time. But the number of calls that you have, or the number of kind of target functions that you have is 3. So what will happen in that case is two will be working at the same time. So as soon as one of them finishes, then you can basically use the third, you can use that thread which becomes available, give it to the third target, and then execute it in that. Okay. Yeah, more workers means less execution time. But one of the other problems is, if you create too many threads, so let's suppose you create like 500 threads, what that could do is, you could kind of end up in a situation where the overhead for managing the threads becomes too high. So, in a real life application, and, if you look at the, with the internet data download or data crawling example that we did, if you create too many threads, after a while, it kind of becomes too difficult to manage those threads. So you end up, you kind of lose the advantage that you gain by multi-threading. So in a real life application, you may not know exactly how many workers you should be using. So you have to kind of play around with this parameter a little bit yourself. I mean, if you have 4 workers for 3 threads, again, you can only put 1 thread inside 1 worker. So even if you're creating 4, let's go ahead and try that, but I don't think that'll give you any advantage, because you would have an advantage if you kind of split this into, if this function was kind of divisible across threads, which I don't think it is. So let's see, it will not give you any advantage. 1 thread is just going to be waiting idling, so you can get like 5 seconds. Okay, we see again you have 5 seconds. So, but again, in a real life application, you generally do not have thread functions that you're writing yourself. You generally have functions that behave randomly, take random times to finish. So you have to play around with this parameter to figure out which one is the best to use. Okay, pointing that out. Okay. Okay, so now I'm going to quickly cover the examples of the book as well, because we did, again, just to illustrate the concept of the deadlock. So let me just open those up, and then just give me 1 second. Okay, so what I want to do next is just copy paste the example 1 from chapter 12 of the book. I'm just going to copy paste that here. Right, so this is chapter 12, example 1. Let's quickly look at this example. Now that you already understand the basics of threading that I just covered, let's go and take dissect this example. So you have a function, call it thread A. Thread starts, And then it says thread A is waiting to acquire lock A. You acquire lock A. So you basically over here, so outside of these functions, you could put this inside a main module as well, but you have you create two locks. So you have lock A and lock B, and lock basically is kind of created using this lock method of the threading class, right? So you have lock A and lock B. You introduce these locks, and then once you have these locks, what you do is so for the first thread, so thread A basically acquires lock 1, and it sleeps for 2 seconds. Then it wakes up, it kind of tries to acquire lock B, and then it sleeps for 2 seconds, and then once it's done sleeping, it basically releases both locks. So you release both locks, lock dot acquire and lock A dot release and lock B dot release. This is just the example one of the book. If you want to copy paste this, just go, if you've downloaded the examples of the book, have you already downloaded those? You should already have these if you've downloaded the book's repo from the GitHub. So if you go into the code repository for the book, so this is the part, book code, mastering concurrency in Python. If you go into that, you go into chapter 12, and then in chapter 12, this is example 1. Yep. Okay, so just open this example 1, and you'll get it from there. Okay, again, so download this GitHub repo, and it'll give you all the code for the all the examples in the book. And if you do not know where the GitHub repo is, let me quickly show you. So it is basically this link here. You can basically go ahead and download the repo from this place, right? So just download the code as zip, right? So this link is here. Posting it in the chat. You can download it from there. Okay, so you get a copy of this, and you can kind of go into this each chapter and kind of show you the examples. And these examples are also mentioned on the slides as well. So if you kind of go into the slides, wherever we're kind of talking about a book example, shown here. So this is chapter 12, example 1, right? So this is the one that we'll be talking about, and then all these other examples as well. Okay. So now that we have the slides open, what basically is happening in this program is, okay, so let's look at example 1 first and see what it does, and then I'll come back to the figure. Okay, so what do you think will happen in this code, right? So thread A, whenever you call thread A, so as soon as thread A starts, it's going to acquire lock A, and then it'll sleep for 2 seconds. And thread B, what it'll do is, as soon as it is called or it is run, it'll acquire lock B and it'll sleep for 5 seconds. And so the problem will be when thread A wakes up and it tries to acquire lock B, thread B already has acquired lock B, right? So it will not be able to acquire it. Similarly, when thread B wakes up and it tries to acquire lock A was already acquired by thread A, right? And so both of them will kind of keep waiting for the other thread to release the lock, which will not be the case because we haven't really put in any mechanism for that. So we haven't told the program to release a lock after a while if it's not able to do anything with it, or if it's not able to complete. And so that will basically cause the deadlock problem. So let's go back to the slide. So graphically what happens is um, thread A, as soon as it starts, it says, okay, give me lock A, it gets lock A, and then it goes to sleep. Thread B, as soon as it starts, acquires lock B, right? It gets lock B and then it goes to sleep. And then when thread A wakes up, it tries to acquire lock B, but lock B uh, is not available. Thread B already has that lock and it's not going to release it. And then thread B, when it wakes up, in order to finish, it needs to get access to lock A, but it will not get access to lock A because thread A already has lock A. And so both of them are kind of waiting for each other, right? So that's where you get the deadlock. So your program should just then say, okay, I'm just waiting for this, but nothing will happen. So you'll never really get to the finished state. So let's run this and then see what happens. All right. And you see that A is waiting to acquire lock B and thread B is waiting to acquire lock A, and then nothing happens after that because you're in this deadlock. Now, B wants lock A, which thread A has, and thread A is not releasing it. And thread A wants lock B, which right now is kind of owned by um, thread B, and it's not willing to release it. So once it's not willing to release it, it's not, so both of them are just waiting in this deadlock. So this is an example of deadlock and how it happens. Okay, and so it won't work. All right. Right. So how do we kind of take care of this problem? Um, well, one way of taking care of this would be to make sure that the lock is available when a thread actually requires it, right? So in the next example, what is done in the book is, I guess, you could kind of rank resources, but you know what is done in the, so let's see what happens. Let's go and look at the second example and then see what is different in there. Um, so here we immediately acquired lock A, and then we went to sleep, and immediately acquired lock B and then went to sleep, and then we needed the other one and that was not available. So let's look at the second example and then see what is different in there. So if you open example 2 from the book, let me go there and open example 2. Okay, so the order that things happen here is what is different from the previous example. In example 1, thread A acquires lock A and thread B acquires lock B. The way that this thing is done in this example is both of them try to acquire lock A first, right? So this guy tries to acquire lock A, and this guy also tries to acquire lock A. So they basically go in the same kind of sequence. So both of them are going to try to acquire lock A, and if it's available, they'll get lock A, and if it's taken up by the other thread, then they'll just wait for it to kind of come back. And then they will wait for lock B, and again, only the thread which has lock A already is going to get to this stage, right? So if thread A basically acquired lock A, thread B will kind of wait at this particular line. So it will try to get lock A, and lock A will not be available. So it'll just keep waiting for lock A to become available, so it won't move down. Whereas if thread A acquires lock A, it'll sleep for 2 seconds, it'll wake up, acquire lock B, again sleep for 2 seconds, and then release both locks, and then end. Now, as soon as it releases both locks, then lock thread B is going to take lock A, is going to do its thing, and then take lock B, do its thing, and then basically release both of them, and then that's how your program will finish. Okay. So the order does matter. So there's very little difference between the two programs. Make sure you kind of understand what happens here. So this guy acquires lock A, and this guy acquires log B. That's the problem, or that's the part which kind of causes the deadlock, right? So if you want to, so what the book kind of says is, how you resolve this is kind of implement ranking among resources. So whoever gets this lock then gets the next one as well, rather than one getting one and the other getting the other and then both getting stuck. Okay, so let's run this example. Example 2. I'm just going to copy paste this example. Sorry, not example 1, example 2. I'm going to run this as is. All right, let's see what happens. So in fact, I need to stop the existing program. Let's see. Let's just restart the kernel and stop this program, hopefully. Okay, yeah, once I restart the kernel, it basically stops it. So the thread got killed, and now, okay, now let's run example 2. Okay, again, if you're stuck on a thread, just go ahead, and if you're in Spider, just go ahead and restart the kernel, and if you restart the kernel, then that thread should get killed, and you should not have to close Spider in order to um, run the next example. So now if you want to run the next example, again, notice both of them try to acquire lock A first, right? And then whoever gets access to lock A, they will get access to log B first as well. So you're kind of implementing this order. So you get log A first, then you're going to get log B first as well, right? So let's see what happens. Okay, so thread A has acquired log A. Thread B is starting. Thread B is waiting to acquire log A. Thread A is waiting to acquire log B. Thread A is acquired log B, does its thing. Thread A releases both things, and then that's when thread B kind of comes in, right? So thread B acquires log A, waiting to acquire log B, acquires log B, and then it basically releases both logs, right? So you have this order now. So whoever gets access to log A first will get access to log B first as well, and you won't get stuck in deadlock. So that's kind of illustrating how deadlock was kind of, so how it was created in the previous example and then how it is avoided in this example. So you kind of add some sort of a ranking in there of the resources. Okay, let's do it one more time. Okay, again in this run, thread A gets access to log A first, um, and releases both of them. I think for some reason it looks as if, well, thread A is the one that kind of gets started first. So that obviously gets access to the lock first, right? If if you started thread 2 after um, thread 1, then what would happen is, um, thread B would basically get access to the lock first. Okay, so if you kind of reverse the order here, what will happen is thread B will get access first. If I kind of start thread 2 first, and then again, make sure that if thread 1 starts later, then join also is added later, because if I had the join, if I was waiting for thread 1 to join, I would get stuck again, right? Um, because thread 1 would be stuck and it would not rejoin, because it'd be waiting for thread 2 to kind of complete. So I think I would get stuck if I did that. Okay, so now in this case, what will happen is thread B will get access to the locks first. Thread B has acquired the lock, right? Um, and thread A basically waits for thread B to finish. And then again, thread B acquires lock B. Um, and when it releases both locks, then thread A basically goes and then it finishes. Okay. Let me just quickly do that join experiment. So if I do this. So if I start both threads and then I'm waiting for thread 1 to join, even though thread 1 will be waiting for thread 2 to finish, I think it may, I haven't tried this before, so I'm trying it for the first time. But I think what will happen is it may cause the program to get stuck. Yeah, you did get stuck here. Thread B has acquired logs. It's performing some calculation is released. Okay, yeah, actually you didn't get stuck. All right, maybe it is something that we need to think about. But I was thinking we may get stuck, but we don't. It doesn't make a difference. I think if you do a little bit of thinking about this, you may actually come up with a reason for this. Um, but yeah, let's see. But I mean, again, I think you're basically asking the main thread to kind of wait for these. So uh, this is, and then thread 2 is actually on a different thread, or thread 1 is also on a different thread. So they're kind of independent of, if this was the main module or the main thread, it's kind of independent of that. So it's only the main that is waiting for these, but the thread doesn't really have to wait for that to join. So in that case, the order of the join doesn't really matter. And that makes sense, I think. Okay. So that's example 2. Now let me take a look at example 3 quickly. So once we're done with that, now example 3, they basically talk about the philosopher's example. Now I tried this example. So basically, again, here what they're doing is they're illustrating with the philosopher's table how you could get a deadlock, and you do actually get a deadlock. So everybody kind of gets access to one fork, and nobody has two forks, and they just kind of keep doing it, getting stuck that way. Now, the book does provide a solution to this in example 4, um, and I tried this solution and it wasn't working. So even though the book says that you will kind of finish the program, it doesn't really finish. Now, I don't really have time to actually go into the details of why this isn't working. So just you may want to note this down. Example 3 and example 4 of the book, they're not really important. So you won't be asked questions which are exactly about or related to these example 3 and example 4, unless of course I get time to cover them and I cover them in some class, which I don't think I will. So um, so just mark this down. So example 3 and example 4, because example 4 doesn't really work, that's why I'm not really going to cover them. Okay, so you can exclude these and you don't have to worry about understanding these, so you can note that down. Okay, so example 3, example 4 of the book, you can exclude them. Okay, let's quickly move to example 5 maybe. Let's see what that does. So 3 and 4 are the philosopher examples. And again, it's just the philosopher's idea. It's not really a practically important example. Otherwise, I probably would have gone and taken a look at these. So what are we doing with example 5? Now with example 5, um, okay, we're just showing the timing. So I think the only difference between example 5 and example 2 is that with example 5, we just kind of add like a timing part to this. So you just import time, and you're just kind of timing how much time it takes to run the program. So that's all we're doing. So I think with this case, we're just talking about how much time you get by running these threads. I think we've kind of covered these in the previous examples that I already discussed, but let me just quickly go through these for the sake of completeness. So I think, yeah, so this is just the example 2 with the time added, right? So again, both try to acquire lock A first, and then whoever gets locked, so the first thread is going to get lock A, and then it's going to get lock B as well, so, right? So you're just timing this. So let's see how much time it takes. So let's run this example. So it takes about 14.5 seconds. for this example, right? Okay, and we are just talking about some resources of the logs. Now, one thing you could do is if you want to kind of make your program run a little faster, is not include any locks in your program at all. And if you don't have any resources that need to be shared between different threads, then you don't need to have any locks in your program. And you can see in this example 7. Now, what is example 6? Let me quickly see what example 6 does, because it doesn't really, it's not really mentioned in the. Okay, this is example 6. Okay, so example 6, basically what it does is it says, all right, so that's what example 6 is doing. So example 6 basically says, okay, we just ran example 5, and what it does is it takes about 14 seconds to run, right? Because you're kind of waiting for the other thread to complete. So even though you have two threads, you're waiting for the other thread to complete. So your program kind of becomes sequential, right? Because first thread, so thread A acquires the lock, it runs for 4 seconds, and then thread B waits for thread 1 to complete, and then thread B basically runs for 10 seconds, right? Because it sleeps for 5 seconds twice, right? So if you go back and you see here, so thread 1 is going to get the lock, and it's going to sleep for 2 seconds and then for another 2 seconds. So it sleeps for 4. So it basically takes a total of 4 seconds to complete. And then if you look at thread B, once thread B gets the lock, what thread B does is it waits for 5 seconds, sleeps for 5 seconds, then acquires the second lock, and then waits for 5 seconds. So basically, if you add this time up, so you have 5 plus 5, which is 10, and then 2 plus 2, which is 4. So 10 plus 4 is 14, and you see that your program basically takes 14 seconds to complete, right? So over here, you're not really getting any advantage of having multi-threading, right? Because you had two threads and you had to wait for the other guy to release the locks. And so the problem here becomes that um, even though you're using threading, your program is kind of, if you were, it kind of runs or consumes the same amount of time if the program was sequential, right? And that actually does make a lot of sense, because even though you have a separate thread for this guy, it waits for the other guy to complete, right? So it is kind of going in a sequence. So that's what example 6 actually illustrates. So let me just show you example 6. Example 6 basically is just a sequential version of this. So I've already kind of covered this in the previous examples that I gave you. So let's see now. So example 6. Um, Wait a second. Okay. Let's see. Mm, Okay. It doesn't really look that different to me. But again, this is like the sequential version. Actually, you can read the code in more detail yourself. I think this is the same thing. I don't know. Maybe I copy pasted the example incorrectly. Let me open this again. Isn't really much of a difference. Let me see. I might have modified this accidentally. Let me go into the Git repo and see if we have the same file there. Chapter 12. example 6. I don't know, I think they probably forgot or to, I mean, it's the same on the Git directory. And I think this is the same program. Again, I don't have time to check this in too much detail, but it looks pretty much the same to me. Let me kind of compare these. So you have log A, log B, log A, log B, thread 1, thread 2, start timer. Yeah, I think this is the same thing. I mean, there's not much of a difference. I mean, um, if you look at the book, the sort of example that you have is slightly different. Let's just look at the book example. So you have, so example 6. Okay, one at a time. All right, so I think the only thing that is different is maybe they just wait for thread 1 to start and complete, and then thread 2 to start and complete. So I think that might be the only difference. Yeah. So this is the difference. It's a very minor difference. So in this case, you start both threads at the same time, and then they should be kind of completing in their own time, right? Whereas in example 6, what you're doing is you start thread 1, wait for it to finish, and then start thread 2 and wait for it to finish, right? So inside your main kind of module, we don't really have a main module here, but you start thread 1, you wait for thread 1 to finish, you start thread 2, and you wait for but thread 2 starts after thread 1, after thread 1 has finished, right? Whereas in this case, both are starting at the same time. And theoretically, I mean, what we want to do here is we want these guys to kind of run concurrently and then complete, right? Whereas in this case, they're not running concurrently. One has to finish for the um, other to start, right? But because of the lock situation, because this guy will get one lock and then he will get the next lock, what ends up happening practically is that even though this one is started at the same time, it has to wait for the first thread to finish. So this is the sequential version, this is the concurrent version, and what we want to demonstrate here is that both these guys kind of take the same amount of time to complete. And I think so. This was so so yeah. So in this case, you can see that we first wait for thread A to finish, and we wait for thread A to finish, and then thread B starts, right? So let's see if it takes the same amount of time. So this is the sequential version. Again, thread A starts, thread A finishes, thread it takes this, and then thread B starts, right? So thread B is starting, and it waits to acquire the lock, and so you can take a look at the output. Right. What you want to notice is the difference in the output. So here you have thread A first, and then when thread A finishes, then thread B starts, right? So this is completely sequential. And in this case, this is concurrent. Thread A starts, waits to acquire lock A, it gets lock A. Now thread B starts, but lock A is not available. So it just waits to acquire or waits until lock A becomes available. Then thread A comes in, it acquires lock B, and you can see that you get these threads kind of intermixed here, whereas in this case you have thread A first and thread B after thread A, and notice that the time between both is pretty much the same, right? And that is because you have to wait for the locks, right? Now if you had, maybe that's what basically the is discussed in the book as well. So um, but if you had like enough locks, if you had more locks in your system, in your program, um, then maybe you can kind of uh, it may not become sequential, but you have to do a little bit of thinking about these things, right? So this part will be explored in the next chapter, which is for race conditions. I don't think we'll have time to cover the examples of race conditions before the exam, so you don't have to worry about that. at least for now, or at least in this lab. Now, so what if we wanted? So what is the advantage of concurrency? How can we achieve speed up our program? Well, if you did not have any locks in your program, right? So if you got rid of the locks and did not have any shared resources, then of course your program would actually finish earlier, right? Um, and this is what is shown in example 7. So if you kind of go to example 7, which is here. So notice over here you do not have any locks, right? So in these examples you had locks, but if you remove the locks from the picture, and if you remember the examples that I showed you that we did at the start of the lab, if you look at those guys, right, they did not have any locks. And over there we saw that concurrency did give us an advantage in terms of the runtime. It improved the runtime. So let me now quickly copy paste uh, example 7. So notice no locks in the program. How much time will it take to complete? Well, thread 1, thread A will start, it kind of runs for 4 seconds, right? Sleeps for 2 and then another 2. So runs, completes after 2 seconds, sorry, after 4 seconds. And then thread B is also running concurrently, right? It does not have to wait for thread A to release any locks because we removed the locks from the program. And then in this case, if you kind of run the code, you can actually see that it should take, how much time will it take to complete? Any guesses? Thread A completes in 4 seconds, thread B completes in 10 seconds. And they are basically running on concurrent or independent threads. And there are no locks here. Okay. So any ideas? Any guesses? How much time this program will take to complete? So previously it took 14 seconds, right? So it has to be less than 14. Actually will take should take around 10 seconds because thread B kind of requires 10 seconds to run. Okay, so let's go ahead and run this. And you see here took 10 seconds, slightly over 10 seconds to complete. Okay, so this is the advantage that you get. I mean, if you did not have any locks, you did not get any deadlocks, you would not first of all get any deadlocks, you don't have any shared resources here, and in that case, your program will just be controlled by the amount of time that longest thread takes. So in this case, thread B takes 10 seconds, so yeah, it will take like 10 seconds to complete. Okay, all right. So almost at the end of the lab, I think we just have maybe one more example to finish. This was, okay. This is another concept which is about concept of live lock. I guess you can read about this again. This is another scenario where you're kind of describing the concept of the live lock. And what happens is it's kind of like an alternate version of a deadlock. So something similar to a deadlock. In a live lock situation, the process or threads in the concurrent program are able to switch their states. So they basically switch states concurrently, and they simply switch back and forth infinitely and no progress is made. So you can kind of switch one, make one active and then the other could be sleeping, and then take the one that is sleeping and make it active and the other guy goes to sleep. Um, but again, if you are working with shared resources, you could end up in something with a situation which is similar to a deadlock, right? So you have the example is that is given here is like you have two spouses or a husband and wife that are really polite to each other. So even if one spouse is hungry and wants to eat, they still leave the fork on the table if their partner is also hungry. So this specification is at the heart of creating a lifelong process. When both are hungry, each will wait for the other to eat first, creating this infinite loop in which the spouses switch between wanting to eat and waiting for the other spouse to eat. So it's kind of waiting for each other, right? So I guess you can run this example yourself and see what it does, but it will kind of keep looping infinitely, it won't really stop, right? And I think you can kind of understand this code yourself if you want to. It's not that difficult. So I'm not really going to cover this in class right now. I think I already covered enough Python for today, and if I try to cover it, I'm pretty sure most people won't be listening anyway. So let me stop here. This is the last example, so you can kind of go through this yourself. And this is written um, in the slides as well. So these examples are mentioned. Again, just remember example 3 and example 4. Uh, example 4 doesn't really work, so you don't have to worry about these two. So don't worry about example 3 and example 4 of chapter 12. Uh, so let's write this again. If you have an older version of the slides, you may not see this, so you may have to kind of add this on your existing slides. Uh, these do not work, so I'll just write leave out or exclude it because again, for some reason, example 4 doesn't really do what it's supposed to do, so I'll just exclude this, so note this down. Okay, 5 and 6 covered, 7 was covered. I, I was 8 is left as a homework. I mean, you can do it on your own time. Now, so in the next lecture, I'll probably just go through the theoretical concepts again, so you kind of are able to connect the code with this part, and then this these slides on race conditions. This is chapter 14 of the book. So race conditions are given here. So I'll cover the race conditions in class, so you can kind of go through these. I may not have time to actually cover uh, all the Python examples. Maybe we will do that in the next lab, but that's immediately before the final, so I'm not sure if I'll have time to do that now. One of the other things that you may want to note, I think the example numbers in some cases are not right. I mean, I think this is not chapter 4. This should be chapter 14. But I will kind of rectify these when I actually get to the chapter, because again, this says chapter 4, example 9. I think this is chapter 14 or something. So these example numbers on the slides are not 100% correct, but I'll actually take a look at these when I actually go through the examples and then I make them correct. Because in the original, again, this was written as chapter 4, example 2. It's actually not chapter 4, this is chapter 12, example 2. So I kind of rectify these or make these correct when I actually go through the Python myself. So hopefully I'll have that done before the next lecture, or at least before the next lab. So just keep that in mind. But um, up to again, this is chapter 12, example 7. Yes. Yeah. So example 7 was this one, right? So example 7 was if you leave out locks, you don't have any locks, you don't have any shared resources, and obviously you will get to see the advantage of concurrency. So yeah, I'll leave that out. So this is chapter 12, example 7. So up till slide number 23, and this is slides which include the Python examples that I've already added, right? So these are updated slides. So up till slide number 23, these example numbers or example references are correct. And after that, at least at this time, the example numbers that you see may not be correct. I will do that hopefully soon, but I just want you to kind of note this, right? So, I mean, you can find the examples. It's just that you have to do a little bit of an effort in the book to actually go and see which example is being talked about here. Okay. All right. Thank you, everybody. Hopefully you enjoyed the lab. Now, I'll probably upload the lab task sometime later today, so you guys can kind of complete that. And I'll share the solution with you as well. Okay, later on. All right. So thank you for coming, and I will see you guys tomorrow in class, inshallah.